Okay, so here we have a small example script that implements equispaced Lagrange interpolation. You can see we're using 80 points here, and we're evenly spacing them across the domain from 0 to 2 using linspace. We're attempting to interpolate the function sine of x, and you can see we're creating the Lagrange bases using the function that we already talked about. Our interpolation then is just simply a linear combination of each of the Lagrange bases, 1 to n, times the value of our function, which we've put as an anonymous function f, at each of our nodes nd. So nd here is the locations from our linspace. So what we can do is, let's first not look at the interpolation and just look at what we would expect for the function itself to look like. So as you can see, it looks like a sine function, as you might expect. So now let's turn on the interpolation and see what this looks like. Now notice this is looking at the same set of points as the exact function. And so notice the size of our y-axes here. We went from sine maxing out at 1, as you'd expect, to now our interpolation looking very, very strange until you realize that the blowing up at the edges is completely distorting this. So if we were to zoom in quite a bit, we could see that towards the center, our interpolation does an okay-ish job of interpolating our function. And actually, we are plotting the exact function alongside of this. So you can see it is doing a quite good job in the very narrow region. I mean, we can't even see the difference between the exact solution and the interpolation in this well-behaved region in the center. But it's easy to see that at the outside we're getting very strange behavior. So if we zoom in on this particular area, we can see we're getting all manner of numerical oddities. So this is an example of what's called Runge's phenomenon. So let's explore that further analytically.